Okay, so the next topic that we are going to cover is representation of knowledge. So what we have done till now is basically we have seen many places where you need to use knowledge. First of all, we have the expert system, knowledge based systems, all the planning programs, um, and a lot of uh, uh, practical applications where you need to use knowledge representation. So what we are going to see here is how we can use some type of flexible representation depending on our needs in the particular domain we are going to work on. So this is what is known as the ontological engineering. What are the different concepts we need to use? So in this place you have what is called the upper ontology, which is given over here. So you can see each link indicates that the lower concept is a specialization of the upper one. So this is what is called the upper ontology of the world. So you have anything, then you come down, etc. Okay. So what we need is something like a general purpose ontology in many cases. For example, if we take an expert system to carry out a certain task, we need to see what are the characteristics of the program. Do we need to take time into consideration? Do we need to take resources into consideration? Do we need to take some type of measurements or mathematics into consideration? Do we need to take something like you know, numbers, you know, whatever, etc. So there are many things. Or do you have complex objects? Okay, for example, if you take a car, okay, so you can call car a complex object which consists of the wheel and the bumper and the axle and the wheels. All these together will form your car. And it's not only just these objects, but the way they are sort of related to each other, right? You need to know how the axle connects the wheels and how the etc. Right? The steering is connected to whatever. Then you have the engine, where the engine is, where is the bumper. The whole thing together forms a complex object. Do we need to use complex objects? Okay, so these are what are called the representational issues which we need to take into account. So what you find is it may be necessary for you to use something like time as well as spatial layout and other types of ontology, and they need to actually work well with each other. So that's what needs to be done, right? So we'll look at some general purpose ontologies. So the first one is what is called categories. Okay. So you can organize objects into categories. Okay. So we can say, for example, you can have a category which says balls, okay, or basketballs, etc. Okay. Or you can say tomatoes, right? Tomatoes, you can say tomatoes is a category, okay. And so once you know that it belongs to a certain category, you know certain characteristics of that category. For example, if it is a tomato, you know that it will be round, it will be red, it will be edible, etc. Right? So if you look at, there are two ways of looking at this. Okay, if you know that it is a tomato, then you can say that it has all these characteristics. Another is that if you are able to, from perceptual input, say something like it's green, it's this shape and whatever, you may be able to find out what is the category you're talking about. For example, it may be a watermelon, say, right? So looking at the from the perceptual input, you can see what are the properties of the object and therefore what is the category it belongs to. Okay. So how do you represent categories using first order logic? You can use predicates and objects. So, for example, you can say that there exists some B and basketball B, okay? Or you can say that B is a member of the category basketballs, member B basketballs, okay? So, what is basically done in most cases is to say that B belongs to basketballs, which is saying that it's a member of the category basketballs. So B belongs to basketball is what is used over here. Also you can have subcategories. Okay, so you can have, for example, you can have a category called basketballs and you can have a category called balls. And you can say that basketball is a subcategory of the category balls, right? Or a subclass or a subset, whatever you want to say. And in categories, you can have inheritance allowed. Okay, so if you have a category, if you have the subcategory will have it can inherit properties from the category. So suppose we say that food, you have a category called food and all food is edible, okay. Then we come to the category of fruit, okay, and we say fruit is a subclass of food and apple is a subclass of fruit. So then looking at the inheritance, we can say that apple is edible because edible is a property of food and therefore it is a property of fruit, it's a property of apples, etc. So the individual apples inherit the property from the food category. And using the subclass relations, you can organize categories into a taxonomy. Okay, for example, you have taxonomy of all living creatures, right? Or plants, you have a taxonomy of plants. So that is the subclass relations that have been used. So all the living and extinct species, right, are put into a single hierarchy, right, getting taxonomy. And also library, you have the Dewey Decimal System, and tax authorities have developed extensive taxonomies of occupations, commercial products, etc. Okay, so you can use first order logic to state facts about categories, right? So let us see some examples of this. An object is a member of a category. So a particular object BB9, so that is one particular ball, right? It belongs to the category basketballs. A category is a subclass of another category. So basketballs is a subclass of balls. All members of a category have some property. So if X belongs to basketballs, it means it is spherical, right? So we could say, for example, if X belongs to the category tomatoes, then it implies that red X and round X and say sweet X or whatever it could be, okay, and edible X. So this type of thing. Members of a category can be recognized by some properties, right? You have some properties. So, for example, if we are talking about basketballs, okay, some X belongs to the basketballs, then it is orange X, round X, and the diameter is 9.5 inches, and X belongs to the category balls. Okay, so you can recognize by these properties. If the object has these properties, then it is a basketball. A category as a whole has some properties. Dogs belongs to domesticated species, etc. Okay, so once you have categories, okay, um, each category will have certain objects in it, right? So now if you have two categories where no member of one category is a member of the other category. So if it is a member of one category, it's not a member of the other category. Then you say the two categories are disjoint. So they don't have any member in common. The second one is what is called the exhaustive decomposition, which means that, okay, here you say two categories are disjoint, but if you take any um, so for example, if you take males and females, right, they are disjoint, but also anyone who doesn't belong to the male category must belong to the female category, and anyone who belongs to the female category doesn't belong to the female, must belong to the male category. So that is, it forms an exhaustive decomposition of the animals. And if you have a disjoint exhaustive decomposition, it is called a partition. So for example, if you have category of animals and vegetables, you can say they are disjoint because it can either be a member of animals, it can either belong to the category animals or it can belong to the category vegetables. And if you take North Americans, okay, the North Americans have to be either Americans or they have to be Mexicans or they have to be Canadians, right? So you can say that it's a exhaustive decomposition. So if you're a North American, you have to belong to one of these three categories. And male and female, if you take animals, either they are male or they'll be female. So this is a partition. So these can be defined in this way by using predicate logic. For all C1, C2, if you take two categories where C1 belongs to S and C2 belongs to S and C1 not equal to C2, their intersection is null. So when their intersection is null, you don't have any member which belongs to both. And when you come to exhaustive decomposition, you are saying exhaustive decomposition S and C. For all i's, that is all the members, I belongs to C if and only if there exists some C2 such that C2 belongs to S and I belongs to C2. Okay. So it has to belong to one of those subcategories, and partition is when both are true basically. So categories can also be defined by providing necessary and sufficient conditions, something like this: if and only if X belongs to the category bachelors, if and only if they are unmarried, they are adults and they are male. So something like that. Next is what is called the one object can be a part of another object. For example, the nose is a part of the face, and we can say like Karnataka is a part of India, etc. Okay, and a chapter is part of a book, etc. So you have what are called the part of relationships. So for example, part of So we could say instead of this we can say something like part of Bangalore, Karnataka, part of Karnataka, India, part of India, Asia or South Asia. So, when they say it's transitive and reflexive, if x is a part of xy and part of yz implies part of xz, which means we can take this and we can say part of Bangalore, Asia, and it's also transitive, part of xx. So you can say part of Bangalore, right, like that. The next thing we talk about is the composite objects. Okay, so that means you have objects which are there and there is some type of structural relationship among the objects. So here we are talking about the biped, right? So a biped is a person with two legs, right? So biped of A implies that there are two legs L1 and L2. There exists two legs and a body B. Well, leg L1, leg L2, body B, and part of L1A, part of L2A and part of BA. So these are all parts of the animal A, and attached L1 to the body, attached L2 to B, and the legs L1 is not equal to L2, okay, because you need to have two distinct legs. But then you have also the problem that you cannot have a third leg, okay, a biped is somebody with two legs. So you will have to say for all L3, if you have a leg L3, then L3 is either equal to L1 or is equal to L2. So this is a sort of awkward way of writing this, okay. Or you use what is called the part partition, right. So then, when we say that, okay, you're talking about a set of apples, right? So when you're talking about a set of apples, you can't say the weight of a set of apples, right? So they use what is called the bunch. So you have three apples, say apple 1, apple 2, apple 3. You can call it a bunch of and put all these apples together, okay? It's something like saying all the apples in a bag, right, together. Then you can talk about the weight of the apples, etc. One more concept we need to see is measurements. Okay, so there are a lot of measurements you need to see. For example, length. Okay, so suppose you have a line. What is the length of that? So how do we represent that? We need to see. Okay. So suppose we say it is 1.5 inches or 3.81 centimeters. How do we represent this? Okay, so usually it's represented like this. Inches, you say inches 1.5, centimeters 3.81, etc. Length of L1 equal to, okay. And conversion can also be represented in this way, centimeters. So if we take inches D, centimeters will be 2.54 into D. And measures can be used to describe objects, right? The diameter of basketball 1, 2 equals inches 9.5. List price of the basketball equals $19. D belongs to days. So you have a category called days to which D belongs. Then the duration of D is equal to hours 24. So this is how you represent measures in predicate logic. So like they say, okay, you have represented this, but how do we represent things like degree of difficulty? For example, exercises have difficulty, desserts have deliciousness, poems have beauty, right? We don't know how to measure these things, right? So you cannot use numbers. Um, so what happens is when we are talking about measures here, maybe you cannot put a numerical value to it, but you can order them. Okay, so you can have ordered objects, right? So here is one example given by Russell and Norwig. So they say that you have exercises which are given, okay, in the book say. So you have E1 and E2. So if E1 is a exercise and E2 is also part of the exercises, one of them is written by Norwig and the other is written by Russell, then you find that the difficulty of E1 is greater than difficulty of E2. So you are representing it by some type of order, okay. So when you represent this type of order, you can also say that when you do these exercises, then the expected score for E1 will be less than the expected score for E2. So this is the type of ordering that can be used, even though you are not able to specifically say this is the number or this is the amount, okay. Next we talk about objects, okay. So objects, of course, like you can say they are nouns, like, no, so you, or you can have, of course we talked about composite objects, so we can say mm, apples or so animals, etc., right. So there are two things we need to distinguish between two of these things. One is like you are talking about distinct objects, okay. For example, if you are talking about a zebra, okay, so it is a distinct object, okay. But suppose you take something like butter, okay, so what happens to the butter? You can cut the butter and it again continues to remain as butter to the two different parts, right. Whereas that's not possible with the zebra. So zebra is they sort of distinguish between these two, okay. So they call the zebra to be things and the butter to be stuff, okay. So suppose you talk about individually one butter slice or some such thing, right? Say butter 3, okay. So how do you, so when you say that it belongs to stuff, or it is, when you cut it, it continues to be the same. You can put it in this way: if B belongs to butter and part of P B, okay, so you have P which is a part of B, right? Then P is also belongs to butter, okay. So that is one way of putting that. So you say B, this gives the melting point of B, if B belongs to butter, okay. And there should have been an and here, okay. And you can give some properties. Butter is yellow, is less dense than water, is soft at room temperature, etc. Okay, so basically you can talk about two types of properties. Okay, if you take something like stuff, in the sense something like butter, there are two types of property: the intrinsic property and the extrinsic property. So the extrinsic property will be something like what is the weight, what is the length, what is the shape, etc. And these will not be retained when you do the subdivision, but the intrinsic properties will be maintained, okay. For example, maybe that it is soft, or whatever you can say about the butter, right? But it continues to be yellow, it is soft, it is less dense than water, has high fat content. This continues to be true even when you take the butter and cut it into two parts, right? So there is some difference between this type of category and the category things, right? Next is events. Okay, how do you represent events? So when you talk about events, okay, for example, you're flying from one place to another, filling the bathtub or doing some, going for a walk. Okay, those are all events which took place. So how do we describe events? So you use what is called the event calculus, and that is based on points of time. So, so what is a fluent? A fluent is something which is happening or between 2 points, say T1 and 2, between two time points T1 and 2, T2, you have a fluent. For example, when you are filling the bathtub, keeps on filling, right? So that is the action goes on between this time to this time. So that's what you mean by a fluent. So to show that a fluent is true at some point, you use T. So you suppose you say T at Shankar Berkeley at time T, right? So how do we describe an event? An event can be described, the event E1 belongs to the category of flyings, okay? The flyer is Shankar, origin is San Francisco, destination is DC, right? Or you can write it as E1 belongs to flyings of Shankar from SF to DC. And you can use things like happens E1 at a time in interval I. So I will be something like in a time interval between T1 and T2. Okay. You can also say extent of E1 is equal to I, right? And and I is represented by the time interval which gives the start and the end time. So I is equal to T1 comma T2, where T1 is the start time and T2 is the end time. So we can define all these things, okay. So TFT means that fluent F is true at time T, right. Happens E at I means event E happened over the time interval I. Initiates EFT, event E causes fluent F to start at a particular time T, right? And event E causes fluent F to cease at a time T. Then clipped, fluent F ceases to be true at some point during the time interval I. Restored means it becomes true at some interval in the I. So we can actually get all these things, okay, the axioms. Something like if you have an event T which happens between T1 and T2 and it initiates a fluent F at T1 and it is not clipped, okay, between T1 and T, okay, then you can say that the fluent is true at time T, okay, and happens if an event happens between T1 and T2 and it's terminated at T1 and it is not restored, then it's not true, right. And clipped and restored can be defined in this way. Clipped F T1 T2 means that happens event between T and T3 and then you have some T, right, when it is terminated, okay. And restored means when it is initiated, there is some time T between T1 and T2 when it is initiated, okay. So when you say TF T1 T2, which means this is true between T1 and T2, if and only if there exists some t in between t1 and t2 when it is also true, right? So we'll stop at this point and we'll continue with the processes in the next section.